Version 12 of the Tycho software introduces 3 new methods by which we can perform satellite identification. So I wanted to take just a brief moment to share with you what those 3 methods are and when you might choose one over another. So with that, let's go ahead and get started. Okay, so this is the first of 3 different methods for satellite identification. In this example, I have a single 1-second exposure. So I go to Action View Images, and as you can see, this is the object of interest. So this is a streaked object, and we would like to identify what it is. Now, because this is a single image, we do not know the direction of travel. It could have been traveling in this direction, or it could have been traveling in this direction. So we have to hypothesize 2 different directions of travel. One way to do that is to right-click, choose Create Ruler, starting point here, end point here. Then right-click again and choose Create Track Satellite ID. So we now have one of 2 tracks created, and I can create the second track in the same fashion. Again, right-click, Create Ruler, starting point here, end point here. Create track again, and now we have 2 tracks with 2 different directions of travel. And if I wanted to, I could create a 3rd track here. Right-click, create marker 1, right-click again, create marker 2. So whenever you have both marker 1 and 2 in the exact same position, what you are effectively doing is indicating that you do not care to involve the motion of the object under consideration for the matching routine. In other words, it will simply look at the position of the object. So again, I can right-click, choose Create Track Satellite ID. So we now have a 3rd track, and as you can see, this 3rd track does not have any motion specified. So with that, let's now go to File, Match ArtSats. Give it a moment to complete the operation. So as you can see, these are the results. The first track has the correct identification, the offsets are low, the distance is under 1 arc minute, and the time offset is under 1 second. Furthermore, to increase confidence that this is in fact the correct identification, the position angle of the object matches the measured position angle in the image. The second track, by contrast, does not have the correct identification. The offset in distance is quite high, and the position angle of the object does not match the measured position angle in the image. The 3rd track, even though we did not specify its motion, it does have the correct identification. The offsets are quite low. However, if we had measured its motion, that would have helped to improve the confidence that this is in fact the correct identification. Another thing we can do is to right-click on a track, choose Show Top 5 Matches, and this will bring up any additional candidates in the matching routine. As you can see, they are sorted by the matching rank. So the first candidate here is the one that we care about, and it has the lowest offsets, and as you can see, it has good agreement with the position angle. The second candidate has higher offsets, and the agreement and position angle is not as good as it is with the first candidate. So this is the first of 3 different methods for satellite identification. Now let's go ahead and move on to method number 2. Okay, so method number 2 is a little bit more automated because it allows us to make use of the results from the FastTracker module. In other words, rather than having to manually draw a line segment and specify the motion of the object, that is already done for us with the FastTracker module. So in this example, I have 30 images. They are each 1 second in duration. And what we want to do is simply have the FastTracker identify any moving objects in this series of images. So after I've done calibration, plate solving, and alignment, which I have already done to keep this video short, I can proceed to navigate to Action FastTracker and give it any desired limits on motion and specify standard sensitivity. I click OK, and as you can see, it is already finished. So it has identified one object here in this sequence of images. So this is the streaked object, and we would like to know what this is. So again, as before, I can go to File, Match ArtSats, give it a moment to complete the operation, and it specifies that this object is Globalstar M003. Now the confidence here is pretty good because the offsets are quite low and the motion is in agreement, 322 degrees for position angle, and that is also the case as measured from the FastTracker module. Now, before I go on to method number 3, I want to take just a brief moment to explain in a little bit more detail what these offsets actually are. Okay, so first, the object distance column. I have been referring to that simply as the distance to the object, but more precisely, that is in fact the cross-track distance to the object. So here, as you can see, it indicates a cross-track distance of 0.123 arc minutes. So what we are saying is that the extracted signal in the image at the time that the image was captured is 0.123 arc minutes in distance compared to the computed position of the known object. And for the second column here, offset in seconds, this is also more precisely known as the along track distance. So here it indicates an along track distance of 0.4 seconds late. That is what the capital L indicates. If it were early, then it would be a capital E. So here again, this extracted object here from the time that this image was captured is 0.4 seconds late relative to the computed position of the known object. Okay, so I want to take just a moment to also clarify the terms cross-track and along track. So I have an example here. So if we have a hypothetical satellite, and this is its orbit, and an observer location here, and we also have the orbital elements of this satellite. And what that allows us to do is to integrate those elements to the time at which an image of that satellite was taken. Then we can say we predict the position of that satellite. So let's suppose we predicted its position to be here. And by the way, the satellite is moving in this direction in its orbit. And let's furthermore suppose that the observer captured an image of this object and the extracted coordinates of the object in that image is exactly where it was predicted to be. Then both the cross-track and along-track offsets are 0. Now let's suppose that we captured an image of this object and the extracted signal, the coordinates of that object in the image, are such that it is indicated to be at this position. Then we say that it has an along track offset that is early. In other words, it arrived here at this position sooner than predicted. So that is an along track offset. And more specifically, it is an early along track offset. And as you might expect, if on the other hand we image the object and the object coordinates indicate it to be here, then it is considered to be late. It has an along track offset that is late relative to its predicted position. So it is here in its orbit, but it should have been here at the time that the image was captured. Finally, for the cross-track offset, if we have captured an image of the object and the extracted signal of the object, the coordinates are such that it is indicated to be at this position relative to the predicted position, then we say that we have a cross-track offset. So hopefully that clarifies the terms cross-track and along track. So with that, let's move on to method number 3 for satellite identification. Okay, so method number 3 is useful in the scenario where some other observer has generated measurements or observations of an object, and they then proceeded to share with you those observations. In other words, you may not have access to the image data, but you do have these observations and you would like to determine if they correspond to some known object. So with this example, we are first going to pretend as though we are that other observer. So here you can see one single image here. I can go to Action, View Images, and you can also see that this is the object of interest. So what we would like to do is to generate a measurement or observation of this streaked object. So to do that, I zoom in a bit more, and then I right-click and choose Create Ruler, specify a starting point and an end point. And anytime we are working with a streaked object, we always want the observation to be centered at the midpoint of the streak. So as you can see, this is marker 1 and marker 2. They have both been defined, and the midpoint has been computed. So we can simply click on Go To, and you can see that that repositions the crosshairs to be at the midpoint of the streak. So with that, we can now right-click and choose Create Observation, and here you see the measurement has been created. Now ordinarily we might proceed to create 1 or 2 more additional measurements of the object, but we just have a single image to work with, And that is sufficient for this example. So I can click Add to Target List and give it some designation here. I will leave it as the default. Click OK. And at this point, you can see that we can now proceed to generate a report. And that report could be in ADES format, MPC 1992 format, or new in version 12 is support for the IOD format. And that is particularly useful when working with artificial satellites. So I click on this option here, Generate IOD Report. Now, if the measurements had been sent to you in some format other than IOD, you can always go to Convert and choose the appropriate option to convert it into IOD format. So this is what the measurement looks like in IOD format. So we have a single line here for the single measurement, and we also have some information about the observer, latitude, longitude, elevation. So with that, we can now proceed to determine if these measurements or observations correspond to some known object. So I go to TLE Analysis, choose Find Matching ArcSat, and this window should look familiar to you. This is the Fast Tracker Results window, and what it has essentially done is created a fake track from the measurements. So as you can see, no motion has been specified, but it was able to determine what position the track is located from the measurement, and with that, it has correctly identified the measurement as corresponding to Globalstar M003. Now you might notice that the offsets are a little bit higher than what we have seen throughout this video, and that is because the observer location is a bit less precisely specified. So that's kind of a secondary purpose behind this example, is to highlight the importance of the observer location and also, by the way, timing information. So the images, they contain a keyword, dateobs is the keyword, which specifies the date and time at which the image was taken. So always keep that in mind, that you need to have both accurate observer position and accurate timing in order to have low offsets. So that's just part of the formula. So with that, I can show you what it looks like if I update the observer position to be a bit more accurate. So I can go to Settings, Observatory, and choose a more accurate observer position for these images. And then I can choose Report, Generate IOD Report once more. And you can see that the observer position is now more precisely specified. The latitude and longitude fields are updated, so is the elevation. And again, we can go to TLE Analysis, Find Matching ArcSat. So again, we have the same match, and the offsets are now considerably lower because we have updated the observer position. So I have now demonstrated 3 different methods by which we can perform satellite identification. That's about it for today's video. I want to thank you for watching and see you next time.